Now recording. So let's get slideshow from current slide. All right. Any questions on anything up till now? And I think I told you I'm saying this mostly for people listening here. My office hours this week are wacko, and probably part of next week too. I've got to be out of town by this time Thursday. I'll already be driving home by this time Thursday. I'm coming in for my first class, but won't be here for this class or linear algebra. We're flying to Texas, Dallas, for a wedding. One of my nephews, my wife's nephew, is getting married, and the activities start on Friday, so we've got to fly out Thursday. So today's office hours are modified because as this class, okay, that we're doing double duty on. This class we're going to do a double class today because we're missing Thursday. So we're going to go from now, 9:30ish, till 12, and then from 12:15 until 1:30, we'll have our linear algebra. Okay, now and then we'll miss linear algebra and this class on Thursday. So next Tuesday, we will have this class regular time, 9:30 to 10:45, and then at 11 start linear algebra and go until 1:30. So both today and next Tuesday, my office hours don't start at 12:15, but start at 1:30. Okay. Tomorrow's office hours, no change. Thursday, of course, there are no office hours because I've just come in, teach my first class, and leave. And then Friday, no office hours because I'll be in Dallas. Okay.
I was going to ask, are we going to do we're doing math team later on?
We'll do math team today, 3:30 to 4:45. Is that what time we normally do? And then we don't have it on Thursday here. I don't, but maybe Dr. Thomas or someone could. I think she may be in class. So anyway, that's that. Now let's see. So Friday, no office hours because I'll be out. Now next Friday, this hasn't been confirmed yet, but my understanding is I'm supposed to have an infusion next Friday. They're going with a new drug, and with the new drug, they do it very slowly because there's chances of reaction. So I get 300 milligrams of the drug, which isn't very much, over 6 hours. They give it to you very slowly. Well, they first do Tylenol, they do Benadryl, and they do a steroid to knock down reactions, and then they let that get in your system, then they start the drug very, very slowly. And if you do okay, they increase it a little in it, but they say allow 6 hours. So I know at least part of the morning I won't be here, maybe none of the morning, because they've got to get started in the morning, because 6 hours they need to have to finish before the end of the day. So I don't know for certain that's going to be next Friday, but it's supposed to be. And then the following Friday, this is the beginning of this one, so the next Friday I have a full dose, which is 1,000 milligrams. So that, again, could take as much, maybe as 6 hours, unless I did. Yes. And then, so the second dose, I don't know how long. If I do really well on the first one, they may do that in 4 hours or something. So I don't know when they're going to schedule that one either. So my office hours for this week and next week, some days will be normal, but other days won't be. All right, any questions on anything we've done up till now?
You're going to hate me for this.
What's that?
You may be able to just show me later, but I figure I probably need to do a few proofs.
Okay.
Because I feel like I'll probably be doing them the next level.
Right.
I've never really done much with them.
Right.
So maybe we need some one-on-one time or something with it.
Okay.
It doesn't take up this time to do it.
Okay.
If we run across one, you can do it, but
Yeah.
more of just like a general how-to would be good.
Right.
We can do that.
Okay. And if we don't run into things that look like they'd be good, I bet you there's some stuff out there like, I don't know, Khan Academy or some of those things. There's got to be something on the internet now that would probably be pretty good that way too, but I'll let you look for that. But yeah, if we see one, we will try to take advantage of it and do it. Okay, let's see. I've got to get my pen set up. There it is. It's rather strange. Okay. Yep. All right. If no other questions, then example 4 on page 68, section 2.4. And by the way, since we are recording now, and Cameron did ask the question earlier, there's a real good chance that we'll be ready for a test in here. Certainly not Thursday because I won't be meeting, but next week almost certainly we'll have the test on the little bit of chapter 1 we did and what we've done in chapter 2. In fact, just about all of chapter 2. But frankly, to me, this is the core bit of the course. You know, what we're doing now. You're introduced to just about every type of equations, then we'll, you know, hit specific kinds and some other ways of approaching. All right, so example 4, the nonlinear first order differential equation x, y, dx plus 2x squared plus 3y squared minus 20 dy equals 0. Now that looks like what we've been talking about, the form for, and here's Victor. Cameron said he bet you would be here. I think he wanted some buffer so he wouldn't have to listen to me alone. Okay, so we're on example 4 on page 68 in section 2.4. Now, I think you were here last time when we were talking about this class is going to be a double class today, and then Thursday we won't have a class, and next Tuesday it'll be a regular class, but linear algebra will be a double class. But you're not in that one, so you don't care about that. Okay. Now this looks like it looks like it might be what they're calling exact differential equations. What's our test to see if it is? Second?
Is it linear? Is that
Okay. It's a nonlinear equation, but is it an exact equation or not? What's the test? Okay, remember we usually name these?
Yeah,
M of xy. I like M and M's better, but you know that doesn't do well for math. And this is N of xy. Okay. Now, what do we do? What's our test?
Take the partials.
Yeah, take the partial of M with respect to y. Why not? And what do you get?
You would get x.
X. Very good. And then what do we do on this one?
Same thing.
No, not quite, but
Well, with
similar.
respect to x.
With respect to x, take the partial of n with respect to x, and what do we get?
That would be 4x.
4x. Okay? Obviously not the same. Okay? Sort of a big boo hiss there, right? Okay. So, they're referring back to equation 13, which, oh, there it is, right up above. Okay. It says, the first quotient, sorry, from 13 gets us nowhere, it says. Okay. Well, remember that was the next step. Okay.
Oh yeah, we got to try to do.
Yes.
the
You're trying to come up with
n over n or
an integrating
minus
factor.
n.
Right. Exactly. So let's try m sub y, which we just did here. This, by the way, is the same as m sub y. That's the shorthand notation. And this, of course, is n sub x. That means the partial of m with respect to y, partial of n with respect to x. We've already calculated those, and let's take the difference of those, x minus 4x divided by n, okay, n being the big ugly one here.
They said that one didn't get us any.
I know, I'm showing you it doesn't.
Okay.
2x squared plus 3y squared. Most of the time on the test question it won't say, the first one won't give you anything. So you need to, yeah, minus 20. This will be a minus 3x over 2x squared plus 3y squared minus 20. All right. Is that something you're going to want to integrate and use as an integrating factor of x alone?
Of course.
The reason being, the main reason being, you're going to have y's in it, so how is it going to be x alone? So yes, that's why that won't give you anything. So do it the other way. The equation 14, well, okay, we've used equation, seems like they would have given that a number, but it didn't. So what we'll do is do n sub x minus m sub y over m. Okay, that's the second one. Okay, and that holds a lot more promise. That would be 4x minus x. That would be 3x over, and your m sub y, m is xy, and guess what? Yes, that's a function of y alone. So that looks like a good chance, a good choice for your mu sub y. The other would have given you a mu sub x if you could have come up before it. So what is the mu sub y? The mu sub y is the integral, e to the integral of this thing. Okay? The thing we just calculated as our test. Huh?
Which ends up being 3 over y.
Yeah. 3 over y dy. Okay? Now, what is the integral of 3 over y dy?
Would that be? It's going to be natural log, or 3 natural log of y.
3 natural log of y. And you don't need a plus c or anything in here. Just leave it alone there.
Probably move that 3 to the exponent.
That's exactly what you do. You write that as e to the log of y cubed. Why would you want to do that?
So that e and the log go up.
And e of a log is, they undo each other, they're inverse functions of each other, so that's just y cubed. So that's your integrating function. Okay? What do we do with that?
Good question.
You what?
Good question.
Okay. You multiply that by each of the terms in your original thing. That's why it's an integrating factor. So multiply it by here. And your new function now is going to be x y to the fourth, right? Dx plus, yeah,
Can we
2.
keep this outside?
You could, but you're going to have to use it at some point anyway. 2x squared y cubed plus 3y, what? Fifth, right? Minus 20 y cubed dy. Suppose, and multiply 0 by that, and you still get 0. Sorry. Sorry about that. Now at this point, we got to go through it all again. Okay? So I suggest for my purposes, I'm going to erase everything else because we really aren't going to use that anymore. We will maybe hang on to the original equation, differential equation, just as a check or something if we need it. I don't think we will, but just in case we do. All right, and let's go back through the whole works here. Okay. Okay. Now, that's not our differential equation. This we're going to let be our m of xy. This will then be our n of xy. And we go through it all again. What's the first? M sub y, partial of m with respect to y. And that would be 4xy cubed. Very good. And
partial of n
with respect to x would then be 4xy cubed, right? Ding, 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 ding. They're the same. Because all those other terms out there, they don't have any x dependence, so therefore the partial of that with respect to x would be 0. Those are all counted as constant. So, sure enough, we do have something we can work with now. Okay? And where do we go from there? Okay. So we're back now like now, what we want to happen here, sorry. So we want to make up a function f, okay? And what has to be true about the f is given some function f, and that's a function of x and y, by the way, we want, and I hope you don't mind if I just go to this. They like to use the partial sometimes or not. It's just easier to do it. We want partial of f with respect to x, okay, to equal your m, the m function, not the m sub y, the m, okay? So we need to do that first. Partial of f, whatever this f is, we want its partial with respect to x to be that. So I guess maybe it does make sense to use, oops, I went to do this and I forgot my eraser.
This new equation, right? Not the original m, but
The new m, that's why I erased all those others so we wouldn't be getting them confused. The partial of f with respect to x, we want to be m of xy, which is xy fourth. Okay, the pen is pretty slow. So what we do now is write that in sort of differential form, and that would be, let's just write it as a df now, not quite true, equal x y fourth dx. Okay?
so that would be
Integrate both sides. Okay? And this gives us f is equal to, this is integrating with respect to x,
that'd be 1/2
right?
y to the 4th x squared.
Right? Okay? Plus some function, we usually call it h, I think. No, they call it g. G of y. Okay? Because when you integrate this with respect to x, understanding that that can have x and y dependent, but you're only dealing with the x part now, You would normally do a plus a constant, but since you integrated with respect to x, that constant could have been some function of y. Okay, so that's why it's a g of y.
Still could be a constant, but
Yeah, except it was sort of supposed to be partials anyway, so you have to have a g of y. I mean, you have to express it. Okay, and then what the next part of this you think will have to be? Since the partial of f with respect to x, we were expecting to do the m.
So g of y.
Yes, the partial of that with respect to y. And this time I think I will write it this way. No, maybe not. Partial of f with respect to y. Then it's going to be
skip a few steps. It's going to be the integral of n, right?
yeah, that's where we're going to head. But what we want to do now is actually take it. Partial of f with respect to y. There's your f.
Oh, okay.
Take the partial of that with respect to y. Were you saying something?
Would be 2y.
Yes, it's going to be a 2 because 4 times 1/2 would be 2 x squared y cubed plus g prime of y. Right? And at the same time, we want this to be your n. And your n is 2x squared y cubed plus 3y fifth minus 20y cubed, if we wrote it right. Right? Now, obviously, the 2x squared y cubed, same on both sides. Right? So that means your g prime of y, which, by the way, is dg dy, okay, is equal to 3y to the fifth minus 20y cubed. And then write this in differential form, and you have dg is equal to 3y fifth minus 20y cubed dy. That really is, our d's there. Everything's in y now. This gives us a g of y is equal to, what would that give us? Yep. 1/2, or I'm just going to write y6 over 2.
Minus 20, or let's say it'd be 5y to the
Fourth, right?
Plus c.
Yeah, I think here we have to throw in a plus c.
Equals g.
Second?
Equals g.
And that is your g of y, exactly. So let's go back to our f down here. This is the one that's supposed to work, and this now, I'm going to carry it down here. It's the x squared y fourth over 2 plus y sixth over 2 minus 5y fourth plus c. Okay? That should be our solution. Okay? Let's see. Oh, goodness gracious, I turned to the wrong page and went, ooh. Okay. So they got 1/2 x squared y fourth, we did, plus 1/2 y sixth, we did, minus 5 y fourth, and then rather than plus c equals 0, they used a slightly different c, like the negative of c, and they just made that an equal sign rather than a plus. And that's usually what they do.
That's what I said. Which would be more correct? To write it plus c equals 0 or just equals c?
It really doesn't matter at all, except they usually write.
I would say equals c is probably more concise. size because you don't just have a random constant laying around and just kind of put
Right.
it together.
And what that indicates, draw the function, okay, and then this then, the C just is a vertical shift, basically. It's equal to, if C is 0, it's here, it's 1, at the other, and it just moves it around. So I don't think it really matters. Just sort of the standard is to make it equal to 0. The function is always equal to 0. The differential equation is equal to 0 for all this to work, and then the answer that you get is equal to some constant C.
I have a feeling it's going to get more complicated on the other side.
Oh, no, you wouldn't imagine that. Okay. All right. Now, they have a few remarks here. Sometimes these are clarifying, and sometimes they are muddying. So let's see what this is. When testing an equation for exactness, make sure it is of the precise form m of xy dx plus n of xy dy is equal to 0. Sometimes a differential equation is written g of xy dx equal h of xy dy. In this case, first rewrite it as g of xy dx minus h of xy dy equals 0. Then identify your m of xy as g of xy and your n of xy as minus h of xy, using 4, which is way back, way back, your criterion. That's what you use. Okay, so that was a pretty straightforward one. If it's written any other way, set it equal to 0. Move the terms however you need to make it equal to 0. Then use those terms as your m and n. Number 2, in some text on differential equations, the study of exact equations precedes that of linear differential equations. Then the method for finding integrating factors you just discussed can be used to derive the integrating factor of y prime plus p of x y equal f of x by rewriting the last equation as p of x y minus f of x all that dx plus dy is equal to 0.
So, in the form.
Yeah, because your dy is by itself, okay, dy dx, and you have a p of xy dx minus f of x dx, so that is now your, and then you do your m sub y minus n sub x, and you wind up getting p of x, and that's why it works. So if we had started with this one, the other one would have been less magical. Okay, it's pulled out of the hat or some unknown body part to get those integrating factors. Okay, so anyway, interesting viewpoint on that. All right, 2.4 exercises. Do any of the odds 1 through 19. You have a whole passel of them. Don't just do maybe 1 or 2 real easy ones, say, I got this down. Do a couple that might be a little more challenging along with those. Then do some of the odds, 21 to 25. I would do 27. I would do 29. And any of the odds 31 to 35. I would try to do 37 and 39. And there's some discussion problems that would be pretty good to think through. Now, none of those are quite proofs, so they may not fit the criteria before. But I know in linear algebra there's going to be lots of proofs, so if we can't find them here, or did you want to find some here too? Okay.
Just in general. Need one.
Right. And then there's a mathematical model. And this first one, number 45, in fact, I guess it's the only one, really holds some interest to me. because of something that happened to me in the Navy, a falling chain. A portion of a uniform chain in length 8 feet is coiled around the peg edge of a high horizontal platform. The remaining portion hangs over the rest. Okay. Suppose the length of the overhanging chain is 3 and chain weighs that, and that the positive direction is downward. Starting at t equals 0 seconds, the weight of the overhanging portion causes the chain to uncoil smoothly and fall to the floor. If x of t denotes the length of the chain overhanging the table, sorry, then it's talking about the differential equation there. And as you can imagine, the velocity increases because you have more weight pulling down. And actually, when I was in the Navy, we were getting ready to go into the yards. So they sent a team out. And of course, Navy always abbreviates things. It's called INSURV. And it was meant Inspection and Survey Team, to test all of our systems to see which ones needed to be serviced when we were in the yards. So I was in the deck department, and one of the things they wanted to test was the manual anchor brake. Okay, they had a mechanical anchor brake, of course, but in case that failed or power went off, would we be able to stop the anchor with the mechanical brake? And of course, we never had to use it, so no one had ever tested it. It wasn't really a good way to test it, so they wanted us to test it. So I was up there on the forecastle. You know, the anchors hold either side of the bow. There's a hose pipe going down either side, starboard and port anchors. And I was on the forecastle. My phone talker was here, and we were in communication with the bridge, and the inspection survey people wanted us to let so many fathoms run and then break it, and then let so many more and break it, you know. And we did the first time, and we had a big, strong bosun's mate there, you know, operating the manual brake, and it ran down, and he twisted and turned. I could tell he was really struggling, but he got it to stop. He said, okay, we just need 2 more. That was pretty hard to get it to stop that time. Well, yeah, we just need 2 more. So I let it go again, and then, yeah, I mean, he cranked and finally got it to stop. Okay, it was so many fathoms. All right, 1 more and we'll be through. That was awfully hard to get it to stop that. Well, all we need is 1 more. Okay, so let it go and then stop it, because by this time more chain had gone through than we had wanted to, so it was really going fast. So he cranked, and he could not get that to stop. So it was just picking up speed, and finally, somewhere below decks was where the chain was wrapped on a spool, and then the very end of the chain was in a bulkhead fastened to the ship. And they always have, and this is true, they call it the weakest link. They put 1 link right before that fastens it to the bulkhead of the ship, and make sure that link is weaker than the ship's bulkhead, because otherwise it pulls the bulkhead out, you know, and that could be a really bad thing to have. And he could not get it to stop. It was going faster and faster. I mean, dust, because, you know, there was rust from years of sitting down there wrapped around the coil, never being used, but moisture and stuff, old paint, whatever. It was, you couldn't hardly see. I couldn't see from where I was what he was doing, but I could hear him grunting and saying, it's not stopping, you know, and stuff. And they said, stand back, and soon that end of that chain at a very high rate of speed, flying into the air, and cut a couple of antenna that were up here. I think it was satellite navigation antenna or something, and came and flopped on the deck and went down the hose pipe like that. I was up here on the forecastle, and I sensed that I didn't have much far to go, because that was you remember on Titanic when they were up there at the very point of the ship? That's the forecastle. I mean, that was as far up as I could go. So I just instinctively, I guess, stepped back a little bit. And when all was said and done, because it was just dust everywhere you couldn't, and the noise was just overwhelming, the chain just running down, and stuff. And someone said, "Look at that." And I looked down, and about 10 inches or so from where my foot was a bowl-shaped indentation in the deck. The deck there was probably 6 to 8 inches of steel, thick, and it was an indentation like a serving bowl indentation there in the deck, not far from where my foot had been. And probably if I hadn't just taken that one step back and that antenna been there, it probably didn't do much. It could have deflected a little bit. There may have been no foot. There may have been no me, It was, and by the way, my phone talker, I had to help him come over the side. He was about to jump, okay? He was getting as far as he could. He was over the side of hanging on to the netting that was there, and I helped him back over because the team said, "I think that's all for today," And we left our anchor in the bottom of the Pacific, out there off the coast of San Francisco. An amazing time. Okay. A good time was had by it. The captain was furious, he said. Coming back in the port, a one-eyed wonder, because here you had an anchor hanging where it's supposed to be on this side, and absolutely nothing except a hole on this side, So they had to repair the anchor.
Was that the supply ship?
Yeah, it was an ammunition ship. Yeah. So, anyway, you didn't need to hear all that, but I didn't know that was the differential equation describing the motion of the anchor. And by the way, each link of the anchor chain was, it seems like at least half a ton, maybe more. And there were many, many links. And the anchor itself was several tons. So there was an enormous amount of weight going down that hose pipe. Faster and faster and faster and faster. Okay, let's move on to 2.5. Hopefully the stories will be shorter here. All right. We usually solve differential equation by recognizing a certain kind of equation, say separable, linear, exact. Those are the ones we've been dealing with. Then carrying out a procedure consisting of equation-specific mathematical steps. That's what we've been doing. That yields a solution for the equation, but it's not uncommon to be stumped by a differential equation because it does not fall into one of the classes of equations that we know how to solve. The best procedures that are the procedures that are discussed in this section, this is called solutions by substitutions, may be helpful in that situation. Notice all the weasel words here. May, usually, sometimes. All right, so what do we mean by substitutions? Often the first step in solving differential equations consists, sorry, I'm reading too much of this, but I know Victor doesn't have a book, and probably some of the people at home don't either, or they might not. Solving a differential equation consists of transforming it into another differential equation by means of a substitution. So this sort of sounds like it's kind of what we did by substitution method in integration. Not quite the same, but it's pretty close. For example, suppose we wish to transform a first-order differential equation, dy dx equal f of xy, by substituting y is equal to g of xu, okay? Instead of y, let y equal u, where u is regarded as a function of the variable x, okay? If g possesses, I'm sorry about my breathing, I'm getting more and more clogged up here. If g of x possesses a first partial derivative, then I better, I guess, clear some space here. All right to erase all this?
Yeah.
Okay. So let's get what we had. dy dx is equal to some function f of xy. Now, just a little bit of a pause here. Certainly if that function f of xy is a product of some function of x times a function of y. Sorry about this, I hate doing this in class, but I can't breathe. Oh, man. Okay. If f of xy was some product function, say g of x times h of y, then separation of variables work. You know, you could write that in differential form and divide by the h of y. And then you have dy over h of y is equal to gx times dx. That would be fine. But probably not, okay? If not, if it's not something that fits, and you know, you could also say, well, could it be linear? Well, it sure looks like it, unless that f of xy had a y squared in it. Then that certainly wouldn't be linear. And could we write it as exact form, which would be then just write in differential form dx minus f of xy dy equals 0, but then the partial of y with respect to x is of course 0, and the partial of this with respect to y would have to be 0, or the minus of that. And the odds of that being the case are not. So if you can't, nothing really you can do to make it much better, then we try something else. And the something is to say, let's let y be some function g of x and u, where u is a function of x. U, this is a weird way to do it. U is equal to u of x, okay? Some function of x, okay? Now, let's look at the g first. If g possesses first partial derivatives, so partial of g with respect to x is defined, and partial of g with respect to u. They're both defined and reasonable and that kind of stuff, okay? Then what we do is take this and you do dy dx is equal to, take the derivative of that. It would be the partial of g with respect to x dx, right? Plus the partial of g with respect to u du dx, because we assumed that u was just a function of x, okay? Now, I left off, they wrote in the dx. I left it off because why? I mean, that's 1. It's obviously 1. So why did they even bother writing it in? So you could write that.
I don't know. Probably has something to do with you're not multiplying that over, you're putting it in differential forms.
Something like that maybe. I don't know. So they write it in, and then the next line they take it out. So I'll just take it out. Go back to what I had before. Okay. I don't know why they put it in there. Okay. But that gives you dy dx is equal to g sub x, and that's a function of x and u, remember, plus g sub u, the partial of g with respect to u, remember that's a function of x and u, times du dx, which is a function of x alone. Okay. Now, if we replace the dy dx by the foregoing derivative, okay, and replace y with f of xy, because remember, no, that's doesn't. Oh, and replace y in f of xy by g of xu. Then the differential equation that started out like this, that was our original differential equation. Boy, they can sure mess up the wording here, can't they? If we replace, becomes this thing. Okay? It seems like they've already said that, but I don't know what, okay. So this thing right here, which is dy dx, this thing, is equal to f of xy, which is f of x, but y is now g of u, xu. Okay. All right. What is that? Okay. Which solve for du dx, solve for this thing. What do we mean by that? We'll subtract g sub x from both sides, and that will give you g sub u du dx is equal to f of x g of u, x and u, minus g of x. No, I'm sorry. Yeah, I'm sorry, that's not g of x, it's g sub x. That's one reason I kind of don't like that notation in there, but I'm trying to do it the way the book does. G sub x, okay, g, partial g with respect to x. And then divide both sides by g sub u, g sub u, g sub u. Okay. Now, now you got your partial view with respect of your derivative view with respect to x to be some, this whole thing here they're going to say is some other big function f of x and u. Okay? Now, of course, what you would try to do is write that in differential form and then integrate. And if you could do that, and you came up with a solution, u is equal to, well, let's have another function name in here. Why not? I mean, we only have used y and f and g and u and now capital F. Let's throw another one in here. Phi, okay. U is phi of x. You remember we said it's just some function of x, but we're going to now call that phi of x. That's going to be the name of that function. Of that last equation, then a solution of the original differential equation is, solution of this one would be y is equal to some g, that's that g, of x and phi of x. Now, frankly, that feels like to me we went through all this just to now change the u from a u to a phi because we did it here. And I think, how has this clarified anything? Okay? Well, don't panic. Don't get too frustrated with it yet. Okay? In the discussion that follows, we examined three different types of first order. Now, these are first order differential equations that are solvable by this means of substitution. which still is as cloudy and muddy as you can imagine. Okay, so let's look at the first. These are three different kinds. We'll do homogeneous equations, have one example, Bernoulli's equation, and then a reduction to separation of variables. Okay, the Bernoulli's equation is somewhat of a new one, except that it looks pretty familiar. It looks a whole lot like your linear equation. And let's go back to the linear equation just to remind ourselves what that looks like. I was looking for the very first expression of it. That was dy. If you go back to page 54, equation 2, dy dx plus p of x times y equal f of x. Well, Bernoulli's equation starts off just the same, dy dx plus p of x y, exactly the same, but now we have, instead of f of x, you have f of x times y to the n, okay? And the n doesn't have to be an integer, it can be any real number. But that's in the future. We aren't there yet, but I'm just saying that's the three we're going to look at. So let's start with homogeneous. Now I know I'm going to need some of this, but I'll rewrite it because it's so taking up the board so badly. Let's get started again. Homogeneous equation. What can you tell me about that? It's going to be something equal to 0 generally, okay? So, here's sort of a definition. They don't quite list it as one. If a function f possesses the property, I'm abbreviating like crazy, that f of tx, ty is equal to t to the alpha, f of xy. Okay? For some real number alpha, okay, then f is said to be a homogeneous function. If that's true, then f homogeneous. Okay? And it's called homogeneous function of degree alpha. Okay, that's where the alpha comes in. Okay. Now, here's an example. F of xy is x cubed plus y cubed. Okay? Excuse me.
So that would be the t, would it be
Okay.
1?
Okay, well, let's just keep it general for now. Let's see what happens if you have f of tx, ty. Well, everywhere you saw an x, you write tx instead. So that would be tx cubed plus ty cubed, which would be t cubed x cubed plus t cubed y cubed, which is equal to t cubed times x cubed plus y cubed, right? Well, this is degree 3, right? Because that's your f of x right here. So f of tx, ty would just be t cubed times f of x, okay? So this would be f would be an homogeneous function of degree alpha equal 3, of degree 3 in this case. All right? Now, whereas f of xy equal x cubed plus y cubed plus 1. That looks pretty similar, doesn't it? Looks like it. But it won't work, because if you do alpha of tx, ty, you get t cubed x cubed plus t cubed y cubed plus 1. Okay? And you cannot write that. You cannot factor out a t cubed because there is no t cubed in the last term. So that's not a homogeneous equation, the first one is. Okay? So, they've given us a real simple one. There are others that, of course, as you were pointing out earlier, I think this could get more complicated. It does, okay. So.
There's no way it can always be zeros.
What's that?
There's no way it can always be zeros.
Right. Okay. So, the first order differential equation in differential form, remember this one, m of xy dx plus n of xy dy equals 0. Okay? Guess what? That is said to be homogeneous if both coefficient functions m and n are homogeneous functions of the same degree. Okay? So if your m of tx, ty is equal to some t alpha of m of xy, and n of tx, ty comes out being t to the alpha of n of xy, and those alphas are the same, then that is said to be a homogeneous function. Not all will be, but if it is, then these would be, then your, this differential equation would said to be homogeneous as well. So you see the 0 part doesn't work. Here the word homogeneous does not mean the same as it did in the remark section at the end of 2.3. Recall that linear first order equation a1 of x y prime plus a0 of x y plus g of x is homogeneous when g of x is equal to 0. So that situation is not the same. This isn't homogeneous just because it's equal to 0. No, that doesn't work anymore. That homogeneous means something else. Something entirely else, okay? So before it was everything's equal to 0. This time that is your definition for homogeneous. Two completely different definitions. And really not related well at all, okay? I guess I ought to write what I just said before. This is homogeneous if m of tx, ty is equal to some t alpha m of xy, and n of tx, ty is equal to t alpha of n of xy. And if these two alphas are the same, then this is a homogeneous form. Okay. In addition, m and n are homogeneous functions of degree alpha. If that's the case, we could also write, oh man, clogging up again. What a day to go, a double day. I can't breathe. I noticed this morning there was no problem except I was coughing all the time. And now I'm not coughing, but my head is just completely clogged up. I think that may be it. I don't know. Or else there's a new set of pollen in the air or something. I don't know.
I know my car has been covered in pollen.
What's that?
I know my car has been covered in pollen. So
This is not the time of year for pollen. I'm wondering if it's dust, maybe, but
I don't know. It's yellow.
it's yellow.
I have a black car, so it's easy to see.
Yeah, you can see it really easily.
Of course, I live off in the woods. So.
Off in the woods. So yeah, I guess ragweed is blooming like crazy, so that could be it. And there's other things that bloom in the fall. So, but you usually think of pollen as more of a spring thing, but the fall pollen must be here. Okay. That's what we need is rain. That's why I said it may be just dust, because it's just everything is powder dry. And I worked in the yard some this weekend and didn't seem to bother me any, but today is much work, like you said. Maybe it's a change of weather too. I don't know.
We can take the break or whatever.
All right. Okay.
At some point.
That's what is the time now?
Oh,
Huh? 10:40. Okay. Well, let's at 10:45. Let's take a quick break. Okay. Or a good stopping point past 10:45. Okay, so this means it's homogeneous. In addition, if M and N are homogeneous, if M and N are homogeneous, which means these two things apply, homogeneous function of degree alpha, okay, like those functions, we can also write this. In addition to this thing, we can also say M of xy is equal to x to the alpha, same degree alpha, M of 1u, and N of xy is equal to x to the alpha, N of 1u. Okay. Time out. What in the world is u? Well, here's what it is. U is equal to x over y. I'm sorry, y over x. I knew when I wrote it, I said that doesn't feel right. Y over x. Okay. All right. Now, basically, that's your substitution. If you think about it, u is equal, with one exception. That's a function of x, y and x, not just a function. Well, wait. No. Y is equal to mu times x. Okay. Sorry. Okay. So basically what we're doing is trying to think of some way to make this seem a little bit more palatable.
Well, I mean, it kind of makes sense. It just kind of helps you, with the first part, settle your exponents, and then at the bottom part, I guess it kind of will help you sort through your N and your M.
Okay.
But we'll just have to see it in an example.
Okay. Here's one way to think of it. I don't know if this is a good way or not, but let's say this t is 1 over x. Yeah. If the t is 1 over x, and it shouldn't be that, it should be just a number. M of 1 over x, y over x would be M of 1u, right? Because u with y over x. But it would be t to the alpha, or x to the alpha, and I guess that would be alpha equal to a minus 1, wouldn't that be?
Yeah.
That would be equivalent to that. So alpha is equal to minus 1. Then that fits perfectly, okay? And that basically is your substitution that you would be using. Okay. Now, not only that,
They go on and on.
yeah, I know. Ew. Okay. I just don't have much room, but I'm going to try to squeeze it in above here. Your m of xy, just like here. Well, let me move it over some. Okay. Whereas I've got it down here, let's do it up here again. M of xy is equal to y to the alpha times m of, do they change the variable? Yeah, v. I thought they would have to be. v1 and n of xy is equal to y to the alpha of n of v1. Same type of deal there, except now your v is, guess what? X over y, okay? And they send you to another place. Well, let's just exercise. Let's rewrite this one. That's what I was suggesting to you. Y is equal to ux, and up here, x is equal to vy. Okay? Y is equal to x, x equal to vy. Where u and v are now the new dependent variables, that will reduce a homogeneous equation to a separable first-order differential equation. Okay? So, yeah, I'm going to have to clear some space. And I hope I don't erase something that I'm really going to need later. Okay, that was just the definition of homogeneous. I think we can get rid of that. Okay, and this was the example of that, which we don't need anymore. And that was the illustration of that, which we don't need anymore. I think maybe I'll need to stop there. I may need that one. I hope I haven't erased something I do need. Okay. So let's start with our standard. M of xy dx plus n of xy dy is equal to 0. Okay, that was our differential form of differential equation. Okay. Now, and let's imagine that we've done our partials of this with respect to y, that with respect to x. They're not the same. Okay? And let's imagine also that we tried our to come up with an integrating constant, and we couldn't come up with one that worked really well. Remember, there are certain things, one of them may not work, but the other one might, but neither one of them works. Okay? What do we do then? Okay? Well, here's something that we could do. So we're starting with that, and what we're going to assume is that the m and the n are both homogeneous. Okay? And if they are, then from what we had down here, m of xy could be written as this: x to the alpha m of 1 u dx plus, and from down here, x to the alpha n of 1 u dy is equal to 0. Okay? Now, guess what? X to the alpha is a constant, right? I mean, alpha may not be a constant, but it's a common term on both sides of the equation. And as long as x is not equal to 0, you can divide it out, right? Huh? Okay. So let's do it. Done. Okay. Divided to 0. Okay. So this gives you m1u dx plus n1u dy is equal to 0. Okay. And remember, this u is this thing down here, y over x. Or the other way to express that is y is equal to ux. Okay? Now, sorry. So let's go back up here, bless you. And since y is equal to ux, this one right here, y is equal to u times x. Let's do a differential of that, okay, for funsies, okay. Dy is equal to what? Good old product rule.
Taking the derivative?
Second?
Taking the derivative?
Yeah.
That'd be x plus u, right? Or wait, are they both, is u a coefficient, or are they both variables?
No, those are, they're variable forms.
Okay, so it'd be x, right, plus u.
How about x du plus u dx? Product rule, right?
Yeah, because the derivative, whatever
Right.
u is, and the derivative of whatever x is, I was just doing like the,
Right. Okay.
reducing it to 1, I guess.
Right. So, now let's so in this equation here, okay, we're going to substitute some stuff, okay. Here our dy, we have what it is. So let's do m1u dx plus n of 1u times x du plus u dx. Okay, and that's equal to 0. All right, now let's get the dx's together, and that would be m1u plus n1u times u dx plus n of 1u times x du. That's a u, that's an ugly, ugly, ugly u.
It's like a W.
Yeah, and w is a different letter. Okay. All right. And that's equal to 0. Yeah. Now, make sure I've done it the same way they did. Yeah, they put the u in front and the x in front. Otherwise, we got it the same. Okay. Now, it may not be intuitively obvious what they did next. But I'm going to come over here to the side and do it. Here we have an x, and here we have a dx, and that's the only place the x is showing up explicitly here. So let's get those together. Okay? So let's divide both sides of this big long hairy equation, every term on both sides, by x here and x there. Okay? Now, while we're doing that, okay, let's divide both sides by the part with u's. M of 1u plus n of 1u. Let's put the u out front. That's what they did. Okay. Dx, and then we'll do that here too. M. Boy, I can't read my writing here. Okay, I think that got lost there. M of 1u plus u n of 1. That u looks like a mu now. 1u. Okay. So these go out here, and that winds up over there. So I'm going to try to rewrite this here. Dx over x plus n of 1u over m.
Wouldn't that be du?
What's that?
Wouldn't the du be still in the numerator? Or are you going to write it out to the side?
I didn't quite hear what you said.
The du, are you just going to write that out to the side?
I'm going to write it to the side, but yeah, m of 1u plus u n of 1u du is equal to 0. Okay? Just because it's just, well, they put it up with it. I kind of like it there. So, now, we've separated the variables here. At this point, we offer the same advice in the as in the preceding sections. Do not memorize anything here, especially that last formula. Rather, work through the procedure each time, and the proof that the substitution x equal vy and dx equal y dv plus v dy plus y dv also lead to separable equations follows from an analogous manner from equation 3. And
Okay,
equation 3 is
so
at the top of the page. What's that?
So from that equation, we'll be able to do more with the problem.
Right. But don't try to memorize the equation. What we try to do is use the procedures, just like we did on that last group, you know, and the integrating factors and all those things. Just do the procedure. Don't try to memorize an answer, because the procedure is what takes you through. Okay? Because I can't memorize things anyway, so I sort of like it. Huh? Yeah. Yeah, it just is too wacko.
I'd rather be able to use it than
Right. Do you want to take a quick break? I think we're past 10:45, aren't we?
Let's take a quick break.
All right. I'm going to pause this here. Okay, we are now back online, and here I start coughing. So let's do example 1. I think I'll clear the board, and let's start from scratch on example 1.
An example? What?
Let's solve this one. X squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay.
assume that they're not going to work as partials.
Well, let's not even assume, okay?
Okay.
All right. Let's first look, though. First thing for something like this, separation of variables. That's usually the easiest, most direct. Let's try it. No way you're going to get these separated because of the plus signs and the minus sign. No way you're going to separate those. So separation of variables out. Obviously, your y, especially here, squared, that's not going to be linear, so don't even try that. So let's see, now the third one, let's do partial of this with respect to y, and that would be
2x squared y.
Just 2y. Partial with respect to y, that's a constant.
Plus.
Yeah. 2y, okay? Partial of this with respect to x is?
2x minus 1.
Yeah. Don't think that's going to work either. Okay. Now, the integrating factor, it might seem like it might hold a little bit of promise, but really I think not, because of those two, the 2y seems the best here, but when you divide, you're not really going to separate this into something just as a function of 1 alone. So I don't think that one will work either. Okay, so let's try this technique. Now, what's the requirement here? They need to be, yes, homogeneous or homogeneous, whichever you want to call it. Okay. Now, what's the test for that? Yeah. If this is your m of xy, and this is your n of xy, then we want to consider m of tx, ty, and what would that be? T squared times x squared plus y squared, which is your m of xy. Yay! That's good. How about this one? N of tx, ty is equal to t squared x squared minus tx times ty would be t squared xy, which would equal t squared times x squared minus xy. Sure enough, that is your n of x. T squared n of x. So your alpha here is 2. In both cases, so yeah, that works.
And so when you do your t's, you just multiply through by t squared because of the x squared, right?
Okay.
That's why you chose t squared.
Okay. It's tx and ty.
Right.
So your tx squared would be t squared x squared. Right. Minus tx times ty. Right. And
So
that'd
it'd
be
be t squared.
yeah, t. Okay, and that gives you exactly that. So basically, looking at this from this point of view, I don't know if this is an accurate generalization of when these things are going to be homogeneous, but think of it this way. The degree of each term has to be the same. This is degree 2, degree 2, degree 2, 1 and 1 is 2. Right. So that's what makes it homogeneous, because every degree is the same. If this had been an x squared y, it's not going to work. If this had been a cubed here with a squared there, that's not going to work. Okay?
All has to be the same.
Yeah. Homogeneous. Homogeneous. You've got all the butter mixed in with the milk. Okay? Right. So yeah, that's what is required. That every term in your m sub xy and n sub xy has to be in x's and y's of exactly the same degree. Okay? And if it is, then it's homogeneous or homogeneous. Okay. All the same. Homo meaning same. Okay. So this is. So we might be able to try that. Now, they are homogeneous functions of degree 2. So therefore, we're going to try our technique, and we don't have to do it from scratch, okay? What we have to do is just begin where we are, and if you go up above, your y is equal to ux or x equal vy. One of those two is going to be what you're going to do. So they say, let's start with y is equal to ux and try it. Y is equal to ux. That's going to be our substitution. Sorry. Okay. Now, your m sub xy, when you use this, that's going to be become m of x ux, basically. Okay?
And u is a function of x, right?
Yeah. Okay. Sorry. So this will be what? This will be x squared plus u squared x squared. You buy that? Okay. And over here, y is equal to ux. That would be n of xy becoming n of x ux would be x squared minus x ux. Well, I keep writing a mu. I don't know why I do that. It's a u, not a mu. They rhyme, they ain't the same. Okay. So that is x squared minus ux squared. Is it or not?
I'm confused why it's x ux.
What's that?
I'm kind of confused as to why it's x ux.
Okay. Your n was x squared minus xy.
Right.
Okay, so this is x squared minus x, and your y is ux.
Okay. Yeah. All right. I get it.
Right. Now, what does this give us but x squared times 1 minus 1 plus u squared, and this is x squared times 1 minus u. Okay? What's that? I couldn't hear. Okay. Okay. All right. Now, remember we substituted here the x's, basically the ux instead of y. But we also got to deal with our dx and dy. So this is produces dy is equal to what?
Du.
Say that again.
Du.
Okay, x du.
Yeah, it would be, wouldn't it?
Yeah. Well, however you want to start. You want to start that way?
Yeah,
X du plus
UDX.
u dx. Okay? Now, let's keep things in order here. The first term, your m of xy, is x squared plus y. Oh, yeah. I'm writing the wrong one down. Okay, that's the one I'm supposed to be substituting. Okay, m of x is this thing. X squared times 1 plus, did it again, u squared. Just something about that. I want to write it a mu.
Y or something.
Okay. That's your m of x, and dx can stay dx. Okay. Plus x squared times 1 minus u. I got it right that time. But our dy is now, x du plus u dx. Okay. Maybe I should bracket this too, so we don't lose something. All right, let's get our dx's together. And that would be an x squared times 1 plus u squared plus x squared u minus x squared u squared dx. Okay, I hope I did that right. Okay, this one was okay.
Yeah.
Okay, this one was this times that. This times that. That's
Right.
x squared u
Then your dx pulled out.
minus x squared u, which is x squared u squared, and that's times dx. I probably need to close a bracket on the left too. Okay. And then get our u's together, and that's just going to be plus x squared times 1 minus u. Oops, x cubed times 1 minus u du. And this is equal to 0.
So how did the x squared go to an x cubed?
Because it's x squared. I kept this at x squared times 1 minus u times x du.
Okay.
X times x squared. It didn't go very prettily, did it? Well, the whole thing went. Okay. Now,
Sleight of hand.
what to note here? You can factor out an x squared here from each of these three terms. All you got are u's left, right? Okay? And that stays with the dx. You can factor out the x cubed here and divide by that, and that will get those together. And then, once you factored out this, all your u's go back together, are together, and divide over here. If I've done it right, that should happen not too badly. But let me make it a little bit easier here. If I'm dividing everything by x squared, then these all go away, and you're just left with a 1 over x here, and that goes away too. And we'll take care of the u's in a second. Okay, so what we have here then is 1 1 over x dx plus, I'm going to just keep them all together and see what happens. 1 minus u is in the numerator here. In the denominator, we have a 1 plus u squared plus u minus u squared. So I see no reason to keep the parentheses there. Can you think of any? And if you just lost the parentheses there, then the plus u squared and minus u squared go away, and you have 1 minus u over 1 plus u du equals 0. You can separate your variables then. You've got them separated, basically. Do you need them on opposite sides? Probably would be helpful. So 1 over x dx is equal to, okay, sleight of hand here, u minus 1 over u plus 1 du. What I did, I subtracted, but I did that by reversing that, and that should give us a second. Okay? Now, I think I can integrate this. That integrates to be log x is equal to, oh boy, what's that? I'm hoping not. Here's how I would suggest doing it. The math team member should come up with his own suggestion. Let's try this. Try this as u over u plus 1 du minus, make that a, yeah, minus du u plus 1. Now, let's take that first one. If we can't think of anything else, let's do a long division on it. That would be u plus 1 into u, and that would be go 1 time u plus 1, be a minus 1, so minus 1 over u plus 1. Would you buy that?
And we're doing this.
What's that?
Are we doing long division because of u over u plus 1?
Yeah. So that looks like it would come up to be the integral of du, that's your 1 part, minus 1 over u plus 1, but you got another 1 over u plus 1, so that would be minus 2 times the integral of du over u plus 1.
We can do that.
I think we can do that. We're running so much out of room. Log x is equal to, this is a u, minus 2 the log of u plus 1. I think I probably ought to have some absolute values in there.
Yes, the same thing.
And somewhere here we need to do something about a plus c, or plus something, okay?
Yeah, I guess this time probably wouldn't be a rearrange and then equal c.
Now, the question is, do we go back and plug in what u is? And what u is, of course, or you are, I don't know, okay. If you go back up here, u is equal to y over x. Okay? That's where that came from. So if you put in a before I go too far with that, let's make sure we're haven't wandered too far astray here. Okay, notice they have the same thing they just did it on opposite sides, on the same side. Integration, they have because they have on the same side, they have a minus u plus 2 log of 1 plus u, and they do have absolute values. So, and their constant they're calling log c. Okay. Right, and that's exactly what they're going to do next. So I'm going to erase something somewhere that I think I can get by with. I think y'all bought this, so I can get rid of our long division here. I've started erasing some stuff here that I hope I won't need anymore. I think so. This was all checking and making sure everything did right, so I don't think we need that anymore. And I'm afraid this next line.
Almost wish there was a better way to add on or extend the slide or something.
Yeah.
You could wipe the screen, but then you wouldn't be able to look back and.
Right. Okay. I think we're through with this now too. I want to hang on to that next one. And I think we're through with this one. So I think we can wipe that clean. Okay. And we probably don't need all that other but since it's there, and let's see if we can do it. All right. So what the way I've written it, and that's not the way they've written it, but they get the log of absolute value x is equal to u, which is y over x, minus 2 times the natural log of y over x plus 1. Okay, plus the log of c.
Oh, the log of C?
Yeah, that's what they wrote as their. And then
I know why they did it.
Yeah, I do too. And I guess since they put a plus there, they have to allow c to be either positive or negative, and then you have to put it in absolute value bars. But all right, now what I don't know. What I would suggest doing here is writing this as y plus x over x. One is x over x. Right?
Okay, yeah.
So that'd be y
I'll
plus
buy
x.
that.
Okay.
Something simple in this.
And then I almost want to get all my logs together and sell them for pulpwood. Okay. So let's just, yeah. Ultimately, they're going to do that, so I'm going to do it here too. This would produce y over x is equal to log x, I'll keep the absolute value there, plus 2 log absolute value y plus x over x minus log c.
Equals y over x.
Okay, and that's equal to y over x. So we're going to combine all the logs together, and here's how you do that. I'm going to skip a few steps here. I'm going to take this 2 here and move it up as an exponent there. And that then would be y over x is equal to the log, natural log of, we'll just do all these together now, x times y plus x squared over x squared.
Over x.
Yeah, I'm sorry. I crossed out too much. Okay, erased too much. Okay, this x cancels one of those out, divides one of them out. Okay, divided by c. But guess what? We could put that c anywhere else we wanted to.
It's a big old hairy thing.
What's that?
It's kind of a big old hairy thing.
It is.
We could say it's times c to the negative 1, which is still c.
Right. So yeah, and here's the other thing they do, and I hope you won't mind my doing this at one fell swoop now. The c and the x squared are in the denominator, so take this off and make
Just write an x.
this c x squared. No, cx, not x squared. I already took off the x. Nope. Okay. Cx. Okay. Now exponentiate both sides, and you have e to the y over x is equal to y plus x squared over cx. Okay?
Then you can
Now,
multiply the cx over.
yes, that's exactly what they do. And that gives us, I'm going to erase some more stuff then. Okay. I guess we're through with this now. I think we remember that y is equal to x. U is equal to x over y. Okay. Let me just erase it all. I don't think we need any of that anymore.
Erase everything.
Yeah, I wish they'd let you break off a portion of the board and say erase all there. But I don't know of any software that does that yet. Okay, I spent all this time erasing, and then I'm going to forget what my next step was. So remind me if I get back up there and say, where was I? Okay.
Multiplying the cx over.
Right. So you have now here, okay. Cx e to the y over x is equal to y plus x squared. I think that's how they got their answer finally. They wrote them on opposite sides. I don't know why they put x plus y rather than y plus x. It doesn't matter. But there's your family of solutions, with c being the constant that varies in the family.
And that's the answer.
What's that? Yeah.
That's the answer.
That's the answer, with c being the arbitrary constant, if you had a initial value problem or boundary value problem you could plug in and see what the c was. Right. Okay, now, although either of the indicated solutions, either with log form or this form, can be used for every, I'm sorry. although either of the indicated substitutions can be used for every homogeneous differential equation, in practice we try to x equal vy when the function m of xy is simpler than n of xy. Okay? It could happen that after using one substitution, we may encounter integrals that are difficult or impossible to evaluate in closed form, so switching to substitution may result in a simpler, easier problem. All right. So that much for solving homogeneous differential equations. Homogeneous meaning the terms, all the terms have the same degree. Okay?
Alright, skip
Yeah.
ahead here now. The next thing we're going to is Bernoulli's equation.
Right.
Is that the same Bernoulli that has to do with viscosity?
Okay.
Or is that a different person?
All
I'm
right.
sure there's a bunch of them.
Okay. Just like C gave you a family of equations, you had a family of Bernoullis. And they were all brilliant mathematicians and physicists, and sounded to be very obnoxious as well. They fought with each other like cats and dogs. Fathers kicked sons out of their homes when the sons beat the father in a competition. You know, it was just amazing. They were so super competitive and egotistical and everything else. There was a Johann Bernoulli and a Jacob Bernoulli. And then there was a son of one of those, and then maybe some other sons and cousins and who knows what all. I don't know which one this is. That would be a good paper topic, perhaps. There's Bernoulli's principle. There's Bernoulli's, like you say, with viscosity. They're just all over the place. And they were very good. And they also helped, even though they were obnoxious with each other, they were pretty good teachers and mentors for others coming up. So several people.
As long as they weren't working with their family.
Yes, right. What was the old saying? You can pick your friends, but you can't pick your family. So let's say I guess they got along some as family too. But all right, so let's move to Bernoulli's equation. If you have this differential equation, dy dx is equal to p of xy. No, that's a plus. I knew that. I don't know why I wrote it otherwise. Okay, bless you. I don't have any sneezing in my classes. Okay, p of x times y is equal to f of x times y to the n.
Be glad it's me this time and not you.
Right.
Because you scare people.
Right. You should see me. My wife screams, the dog jumps. It's just madhouse at our place.
Oh, really?
Yes.
That's great.
That is the form where n is any real number. Notice not just any integer, but any real number. Pi, square root of 3, you know, it could be just about anything. Minus pi thirds, or scary things. Okay? Any real number. That's called Bernoulli's equation. Now it looks, except for that y to the n, it looks like your linear equation. Okay?
I like those.
But with the y to the n there, it's obviously not linear anymore. Okay?
I don't like it as much.
Right. Now, of course, if that was y to the 1, you could then manipulate and get it back. Yeah. Note that for n equals 0 and n equal 1, the equation for is linear. Okay? For n not equal 0 and not equal to 1, the substitution, and here's the substitution we'll use, u is equal to y to the 1 minus n. Now, obviously that won't work for n equals 0, and it won't work for n equal 1. So don't try to plug those in.
We wouldn't need it to work then, would we?
No, we wouldn't. Absolutely not. So don't do it. Okay. But for n equal any real number, especially not a non-integer number, that's going to be what you have to use. And if it's any integer other than 0 or 1, you're going to have to use that as well. And remember, those could be positive, negative fraction, decimal, rational, irrational, it doesn't matter. Okay, so if you use that substitution, it reduces any equation in the original form, this form, into a linear equation. So they say. All right, so let's see if we can solve this. Here's example 2. X dy dx, okay, plus y is equal to x squared, y squared. Now,
it's not equal to 1 or 2, so we can use substitution here.
Second?
It says it's not equal to 1 or 0, so we can
Yep.
use that substitution.
Yes, but what do we need to do first? It's not quite in that form yet.
We need to, can we divide by the x? Is that what we
Do
need?
what?
Divide by x?
Yes, exactly. Divide by x. So that will go out. This will be y over x, or y to the x minus 1, and this will just be x to the first power. Now we've got it in that. Let me rewrite that. Dy dx plus x to the 1 minus 1 y is equal to x y squared. And sure enough, as you said, the n is not equal to 0, it's not equal to 1, so therefore we can use Bernoulli's. It is a Bernoulli's equation now, and our substitution is let u equal what?
That's going to be y1 minus m, which would be 1 minus 2, right?
Right? 1 minus 2 is?
Negative 1.
Negative 1. U equal y to the minus 1. 1 over y. All right? All right. Now, what do we do with that? Okay. What I would be tempted to do first, this implies then that y is equal to u to the minus 1. Reciprocate both sides, right? Okay. Now, let's rewrite this then as dy dx. Let's do this. Dy dx would be equal to
xy squared.
second.
Xy squared. Or wait, you would want to do x.
Yeah, I'm doing over here. That y is equal to u to the minus 1. That would be minus u to the minus 2 times du dx.
Okay, why would it be a minus u?
I'm sorry?
I see the negative 2, why it's, to the negative 2 power, but why would it be minus u?
Take the derivative of this is the exponent times the coefficient is the minus 1. Drop that by 1.
Okay, so you just took the derivative. All right.
Yeah, I'm taking the derivative of y with respect to x.
Okay.
And that takes the derivative of u with derivative of u times derivative of u with respect to x, du dx. It's sort of chain rule.
Sorry, I thought you were doing something else. In a different, I was out in left field.
Yeah. Well, I'm not sure. I'm not either. I'm not sure this is how the book is going to do it, but it just seems like a logical thing to do here. Okay. So we've got dy dx Let me make sure I'm not going crazy with it.
So you can plug in u for dy dx. That's the point.
Yeah, right. Okay. So that's what our dy dx is. I'm just going to do term at a time. X to the minus 1 y would then be x to the minus 1 u to the minus 1. Okay? And xy squared would be x times u to the minus 2. Okay, so let's rewrite our differential equation to be minus u squared, no, minus u to the minus 2, du dx plus x to the minus 1 u to the minus 1 is equal to x u to the minus 2. All right. I'm beginning to think some things may be separable now. Not sure I like these exponents. Maybe I'd like it better if I saw them in denominators.
Let's see, that'd be negative 1 over u squared. And
Okay. Let me see that. Minus u squared du dx plus.
Oh, you're just going to throw everything in the denominator.
Second.
Shouldn't that be?
Oh, that's a minus. That's a minus. I can't read my sign. Okay.
That should be over. Just
Yeah.
1 over it.
Yeah. Okay. Okay. Minus 1 over u squared plus 1 over x u equal x over u squared.
I don't know if that makes me much happier, but
Right.
well, you can multiply u squared by on both sides, right?
That's what I was going to do to see if we can make life easier that way. So multiply by u squared. That would give us a u up top and that. So now we have a minus du dx plus u over x is equal to x.
Divide by x, you get 1. That's probably not fair. Or multiply by x and you get x.
Okay, I'm beginning to think this isn't separable now. And maybe it doesn't need to be. Let's just get the minus out of there and du dx minus 1 over x u is equal to minus x. Now that is a linear equation. That's all we were promised, that it's going to be a linear equation.
And the p of x being like 1 over x, right?
Right. So you just identify it. Then p of x is equal to negative 1 over x. What do we do with that p of x? For linear equations? Integrate it. Okay, reminder. This is back at the beginning of this section, I think. Yeah, 2-3. And I'm closing up again.
Oh, and then we raise it to e, that's right.
Yes, you
So
you integrate it first and then raise it to e.
So it's going
And
to be e to the x.
So this would be integrate this, a minus 1 over x dx, and what would that be?
Negative natural log x.
Natural log of x. Guess we have to put that is, and we don't worry about a plus c at this point. And then you raise this, and when you raise So that, strangely enough, becomes the log of 1 over x, right? And e to the that would be 1 over absolute value x, right? That's your integrating factor. And I'm hoping we can just drop the absolute values. Trying to find where we are now. Do they?
They just leave it x to the negative 1. They don't even do absolute values. They don't keep up with it.
Yeah, they don't do absolute values. That's what I was looking for. I couldn't see it. Okay.
Kind of like, how do you know when you're supposed to be responsible for them or not?
Right. So 1 over x, or x to the minus 1. Okay. Now, let's erase some stuff. This was our generic form. We've already got that taken care of, I hope.
Isn't it funny that we found the p of x and it turned out to be the p of x we started with?
Yeah, that does look strange, doesn't it? No, but this is the integrating factor. It's not p of x, it's the integrating factor.
But it's still the same as your p of x.
Well, but not quite, because it's 1 over x. Wait, is it? Yeah, it's, and the p of x is minus 1 over x, yeah.
I didn't see you sign.
Yeah. And I think we've already used this too, so let's get rid of it. Okay. I don't know if we need that anymore or not, but we'll pretend we don't.
We've got about a minute left.
Oh, really? You. Okay, let's see if we can close this out pretty quickly.
Because you said this one's going to end at 12, right? And then the next class goes from 12:15 to 1:30.
Yeah, that's right. Okay. Yuck. Okay, we've got our integrating factor. We multiply that factor, 1 over x, by every term on both sides then, don't we? This will be 1 over x dy dx
Is it not du anymore?
plus, second?
Is it not du anymore?
Oh yeah, you. I can't read my writing.
It's right over. Wait, no, it
Then
should
I
be
surely
du.
can't read my writing. Okay,
It should be
du.
du dx, not d dy du. It should be du dx.
How did it? Oh, there it is down there. Okay, I was looking at the wrong form. Okay. Sometimes it erases and sometimes it don't. Okay, let's start over. I probably should look at the right equation, which is this one down here.
So that would be 1 over x.
Yeah. Is that the one we wind up with, or do we wind up with this one?
With,
Yeah, but
du dx minus 1 over x for u equals negative x.
yeah, but
And our integrating factor was 1 over x.
right. But
Plugging it in, right?
okay, what's our differential equation now?
That was it.
This one down here at the bottom, isn't it?
Yeah, yeah.
Yeah.
And
Okay.
I just have the-
So those up there are just
separate.
being, they're in the way. So let's get them out of the way. Okay. And we've done all that, I think. And, okay. I don't think we need this one anymore. And I don't think we need that one. I hope I'm not going to erase something I really do seriously need.
I would leave 1 over x.
I'll leave that. I'll take off the absolute value bars. Okay, that's our integrating factor. So, we multiply that by this. So that would be minus 1 over x du dx. Or do we need that next equation? I think that would be better. This one.
It's the same thing.
It is the same thing, but
Well, except
missing a
that
minus
one's
sign.
minus.
Yeah.
You just,
So
yeah, you just move the
terms
multiply
around.
by
Yeah.
-1.
So I think now we got it. I think. Why did I leave that one above it? I'm not sure. Let me erase this one too. Well, it's not doing anything now. I think I've confused it. Okay. I've got the electrons running in circles. Okay. I think that's my equation now. Boy, I could have just rewritten that.
So it ends up being
See, 1 over x du dx minus 1 over x squared u equal -1.
That's what I
Got it. All right. Now, supposedly this on the right-hand side is a perfect, that's a product rule, right? This is d by 1 over x times u, I believe.
Yeah. Because it would be
Because it would be 1 over x du dx minus 1 over x squared u. Right. So I guess I could put a d by dx here. And this is equal to -1. So now we write it in differential form. D of u over x is equal to minus dx. So this is, when you integrate the two sides here, in fact, let me change that ever so slightly. To do that, then you have u over x is equal to minus x plus c. So u is equal to minus x squared plus cx. And u is, I knew I was going to regret that, y over x, if I'm not mistaken, right? No, that's a different u.
y to the -1.
Yeah. Y to the -1. So this would be, rewrite this, it would be 1 over y is equal to minus x squared plus cx. So,
Reciprocals, right? Reciprocate both sides.
yeah, that's a mess, but I guess you can do that. Y is equal to 1 over cx minus x squared. That's probably not the way they have it, or is it? Yeah, it is. That's how they leave it.
Well,
They left it minus x squared plus cx.
we may need to get some medicine because we're matching up with what the book does for all that.
Yeah.
Must be
I'm
something.
beginning to think I must be thinking weirdly if I'm agreeing with the book. All right. So we saw Bernoulli's. Next time we'll get it to reduce to a separation of variables.
Don't forget to stop screencasting that.
Right.
I'm going to run down the restroom before starting this.
Yes. I'm going to go get something else for my throat.